Hi Wanderers, welcome back. This is another video on how to identify minerals and crystals on your own at home, in the field, or wherever you may be. Waiting for Nate to join in. There we go. Hello! Alright, let's get started. So in this video, we're going to be talking about cleavage versus fracture, and I think I have to move this table a little bit. Okay. Cleavage versus fracture, and which one is better to do, better or more useful or better for you, essentially. Alright, for this one, I brought out a whiteboard because cleavage and fracture can be a little bit challenging in terms of like conceptualizing them. So it also isn't like super clean cut and simple. Like a lot of the time, Mohs or luster, for example, or other categories we've talked about so far, those, while there can be some leeway between the groups, it's generally pretty visible what we're observing. But cleavage and fracture can be a little bit more subtle or hard to find. So we're going to talk about it. Hopefully you guys can see what I wrote on this whiteboard. Okay, so cleavage, I think I'll have to flip it around. Tee-hee. So cleavage, we'll talk about kind of some properties of cleavage and then some properties of fracture. We're going to compare them just a little bit, compare and contrast. And then once we're done talking about those properties, we will discuss which one is more useful. So we'll get started. So cleavage, as I've wrote here, it creates minerals that exhibit cleavage. They'll break into pieces that have smooth or flat surfaces, and they're very often parallel to each other. Parallel just means that they're side by side. Your fingers are parallel to each other. They run in both directions. This occurs because of the alignment of weaker bonds within the crystal lattice. What does that mean? So here is a very crudely drawn diagram of muscovite mica that I've drawn. So you can see in this muscovite mica, there's these very strong chains of silica and oxygen and whatever else is in there. I can't remember the third one. There's a couple. It's mostly silica and oxygen. And then you've got these large bonds of potassium that link these sheets together. So what we can take away with cleavage from this cute little muscovite that I definitely don't want any of my professors to see is you can clearly see where perhaps it would cleave, where a break might happen. You can see visually that there might be some weaker areas. Now, if this were an actual, piece of muscovite, the chain would go on and on and on and on, and these sheets would continue for a long time and just continue to be separated by these large potassium atoms. Why is that important? This is because a crystal lattice, part of the definition of a mineral is that it has to have a definite chemical formula. This is the definite chemical formula, the definite crystal structure for muscovite mica. So this is repeating and predictable. If we have a piece of muscovite mica, we know that the crystal lattice looks like this. So when we're talking about cleavage, muscovite mica is a really good example of cleavage. We'll get into that when we're done talking about cleavage, but smooth, flat, often parallel surfaces, and then it occurs because of alignments of weaker bonds within the crystal lattice. So we can see that. There's clearly going to be some weak points in here. And the cleaving will correspond to the planes of atoms that are less tightly bonded to each other compared to the rest of the structure. And because the crystal lattice will always be the same, always, 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 this is predictable and repeatable, and thus it's extremely diagnostic. So let's grab our piece of mica so that we can take a look at this huge, spectacular piece of mica. Oh, it's so crazy. It's so big. Okay, so mica cleaves extremely readily. You can see that it's flaking off into my hands. If I showed you the table, it'd be covered in little pieces of mica, which is almost inevitable. This is specifically a phyllosilicate mineral, which we can get into the different categories of silicates at another time, but you can see that there are these parallel planes of cleavage on the material. And you can also see where it's kind of actively breaking away from each other. So, this is, I think, the best way to observe cleavage when we're trying to understand it on an atomic level. So there's just millions and millions and millions of these little sheets that make up the mica. And all of these sheets are lattices that we looked at just before, the oxygen silicon lattices, that are bonded by larger potassium atoms. And you can see that that's just really readily separating into even smaller pieces. So I love the example of mica for cleavage. Fracture, on the other hand, we can look at my handy dandy whiteboard. Fracture occurs when a mineral is subjected to stress that exceeds the strength of its bonds, and the surfaces are often uneven, rough, or curved, and usually these are random because they're just stress breaks. So because the breaks from fracture occur because stress is exhibited onto the mineral, these are a lot more random and less predictable. So, oh no, I need my marker for our handy dandy diagram. So, muscovite mica, again, is such a great example because it has such visible, excellent examples of cleavage. So, the difference between these two things, cleavage, is going to happen like this. When muscovite cleaves, when mica cleaves, it's going to cleave like this. That is predictable and repeatable and is very diagnostic. So cleavage is repeatable. This is really important if you're familiar with, other areas of science where part of the scientific method is getting an observation, making a hypothesis, and then you go through certain stimuli, and in order for it to be a valid result for the test, it needs to be predictable and repeatable and consistent. Cleavage is predictable, repeatable, and consistent, and thus cleavage is diagnostic, and this is going to be helpful for us in the field. And we'll take a look at some more hands-on examples that aren't mica, ones that might be a little tougher to look at in a moment. But fracture, because it is just stress-related breaks, fracture would happen some way like this. So because the stress, there's no way to tell the consistency of the stress at hand, it's just going to be random breaks like this, and that just occurs when the stress is too much for even the strong bonds to manage. So we saw cleavage with the muscovite mica. I lost my marker cap. Oh no. So we saw that cleavage with the muscovite mica where it went like this. Fracture would be like that, where I'm applying stress to the mineral in a way that's random, and it's just creating a break in the bond. The force I'm applying is greater than the force of the bond in the crystal lattice that is holding it together. So that is a really fantastic example of cleavage. In the field, mica is super recognizable because of the cleavage. It flakes off and it's just super glittery. It's really beautiful. You can see on the table, it's just glittering everywhere. So that is some cleavage. We'll kind of get into stages of difficulty with them. So the next one that I'll show you is, you might recognize from our Mohs hardness video, this piece of selenite. So I'm gonna show you guys this here. This piece of selenite is a really good example of what we would call perfect cleavage. You can see that it's forming roughly 90-degree angles, maybe a little greater than 90. And it's producing these planes that are pretty much parallel to each other. So you can see it's cleaved here, it's cleaved here, it's cleaved here. So this, these are all parallel to each other, and then they're running parallel in this direction as well. So like here and here. And they're forming these really predictable straight angles that you can measure. In my geology classes, I've had minerals under microscopes to measure the degree of cleavage to identify the material. It can get a bit challenging, especially when you get into materials like, this is an example of labradorite. This is a feldspar mineral. You can see that there's some examples of cleavage. It's not very good, but, ooh, pretty. But here is an example of fracture where it's just jaggedy. There's no way to tell how much pressure or force was applied to create that jaggedy look, and there really isn't a way to replicate this jaggedy edge. So yeah, you have these really flat, even planes of cleavage that you can observe. And this is like a little bit harder of an example. The nature of cleavage gets a little bit into the weeds. And if people want me to go into that, I'm definitely more than happy to. But the bottom line is that cleavage is repeatable, it's predictable. I can't stress that enough. Cleavage will be the same every time for every mineral. It is a diagnostic characteristic of the mineral. Sometimes it can be difficult to see just with the naked eye. A lot of the time, geologists will hold a loupe, will carry like a little loupe with them, little magnifying glass, or you can even bring it back to your house or a lab if you have that, and look through a microscope and measure the angles of cleavage. Cleavage can get a little more complicated. Like I said, it occurs on three-dimensional axes, so it's like an X, a Y, and then like a Z axis. So it gets broken down into subcategories of perfect cleavage, good cleavage, or poor cleavage. And that's represented by 3 numbers in a bracket that are going to be 0 or 1. I don't think that was not as beginner friendly, so I think if we want to go into that aspect of cleavage, then perhaps we'll have a separate video on that that's just dedicated to planes of cleavage and how to identify them. But for now, we'll get into fracture. The most common types of fracture that are identifiable are conchoidal fracture, and that is really, really, really observable on obsidian. Conchoidal fractures are going to be fractures that look like kind of a lot of U's, or they're curved and kind of step down. Quartz can often fracture conchoidally like this too. Obsidian is probably the best example that I can think of. There's even, you can see a couple of conchoidal fractures on the bottom here too. And again, these are stress fractures. You can tell that it is not cleavage, it is a fracture, because there's a bulb of percussion on all of these conchoidal fractures. So you can observe that it was hit. So you can see kind of where those crunches are, and then how it conchoidally fractures. I'm an archaeologist for my main profession, and I pretty much, a lot of my job as a Great Basin archaeologist is to look for conchoidal fractures, rocks that have been conchoidally fractured. So a lot of the time that means obsidian, and a lot of the time that means chert. So chert will also have a conchoidal fracture. Obsidian definitely has the best conchoidal fractures. I could not rave enough about obsidian's conchoidal fractures. But yeah, if you've ever seen Native American arrowheads or tools, you will see that they're flint knapped all over with conchoidal fractures. And that is generally how obsidian will fracture. And even though that is somewhat repeatable, because it's pretty much the only way that it will fracture, unless you get an ugly step like this, which will ruin your arrowhead, unfortunately. Unless you're really good, I suppose. But a lot of the natives were. It was very, very interesting. But it's not really like repeatable and consistent in the way cleavage is, because you can't really say, like, by looking at a conchoidal fracture, you can't really tell specifics about it. Now, a fun fact about obsidian is obsidian's actually not a mineral at all. Technically, it's just an igneous rock. That's because it doesn't have a definite crystal lattice or chemical formula, so presumably that's why it fractures conchoidally like this so readily, is because there is no crystal lattice to hold the bonds together really tightly, like there is in muscovite. Because even when I was folding the muscovite down, you can see that it does, like, it doesn't, like, want to, per se. It can, when you get larger pieces of it, it can be tough to fracture it because those lattice bonds are so strong. So that is the main type of fracture that's going to be helpful to you when you're trying to identify minerals. Pyrite can be another good example of an uneven or a Halite fracture. And that's just when it's kind of all over like this. Uneven is the official term for this sort of fracture. Halite is another word you can use to sound more official, I suppose. But yeah, in case you haven't gotten it, cleavage is going to be much more useful than fracture almost every time, unless you're talking about rocks like obsidian that actually aren't technically minerals, minerals or crystals. But yeah, cleavage can get very, very scientific and very, very specific. As you can see here, you can tell that there's cleavage, but it's hard to say exactly to what extent or what the angle is. So yeah, let me know if you guys want me to go more into depth on cleavage and how to look at it. And we can definitely do that. But I think we'll stop here just for this to be a approachable introductory video to concepts. So yeah, we'll take one last look at my little whiteboard here. So cleavage repeatable, predictable, diagnostic. Fracture, not that. They're pretty much opposite things, but they're both when a material breaks, essentially. Breaks, fractures, or cleaves. All right. Thank you so much for joining me, guys. I had a really fun time with this video. Please let me know if you have any extra specific questions that you'd like me to get into. Otherwise, I will see you in the next one. Thanks so much. Have a good night.